Okay, in today's video we'll be talking about potential energy. Potential energy, or PE, is the energy in an object due to its position. There's two types that we'll be discussing. The first is gravitational potential energy, like this rock has the potential to do work if it fell off this cliff. Just due to its position above the earth, it has the potential to do work. And elastic potential energy. This rubber band, by its virtue of being stretched, has the potential of doing work. Okay, we'll look at gravitational potential energy first. The energy of an object due to its position relative to the ground. So this ball will have more potential energy as you lift it higher. How do you give it potential energy? You have to actually do work because the earth pulls it down. So to push it back up, you have to do work. So the work we're talking about is a force through a distance. So the work of gravity would be the work it uses to get from this position, in its original position, down to its final position. So gravity did this work because the earth pulled it down from this position to this position. So what force did it use? Whatever the object weighed. What distance did it move? HO minus HF. HO being the original position, HF being the final position. And it can be negative too. And it all depends on the reference point you choose, and I'll show you that in a moment. So let's look at it a little closer. All right. Here's our equation for the work due to gravity. mg, which is the force, HO minus HF, which is the distance. If the ball started at 4 and falls to 2, then the work done on the ball by gravity would be positive, since the force and the displacement are in the same position. If the ball started at 2 and was lifted against gravity, then the work would be negative. All right. Work due to gravity is independent of the frame of reference. For example, you could set the frame of reference any place you want. In the previous example, the difference between the lower position and the higher position was this was 4 and this was 2, or the difference was 2. You could set the reference point of any position you would like to make the problem easier. You could set the ground as a reference point, as we did in the previous problem. You could hit the final position as the reference position. You could hit the initial position as a reference position, call this 0 and this -2, for example. Or you could pick any point you want. Any way you do it, the distance between this ball here and when it reaches this position here have to be the same. So you can change the reference point to make the problems easier, which you'll see as we do more problems throughout the chapter. So what is the definition of gravitational potential energy? Gravitational potential energy, or PE, is the energy that an object of mass m has by virtue of position relative to the surface of the earth. That position is measured by the height of the object h and its relative position to some arbitrary reference point that we called 0. So how do we calculate potential energy? It's just simply force through distance, force being the weight, times the distance. So this would give us the potential energy of an object at any position or above any position that we happen to use as a reference point. So what is the unit for potential energy? It would be the joule, and the reason being is it would be mass times gravity is a unit of a Newton, right? It would be kilogram meter per second squared times a meter, or a Newton meter, which is a joule. Let me say that again. This would be a kilogram. This would be meters per second squared. So those two together would give you a Newton. Height is measured in meters. A Newton meter is defined as a joule, as we talked about in previous videos. All right. So let's try a problem with this. Gymnast leaves the trampoline at an initial height of 1.2 meters and reaches a maximum height of 4.8 meters before falling back down. What was the initial speed of the gymnast? Alright, when we're done with this problem, I want to change the reference point. For example, how high did this person actually rise? Well, he rose 4.8 minus 1.2. Why don't we just say, call this 0 in the future, and this some other arbitrary height, what's 4.8 minus 1.2? That would be 3.6. So we could have called this position 0 and the top position 3.6. But for argument's sake, we'll leave it how it's depicted in this problem. Okay. What is this equation? If you remember from previous videos, the work done on an object is equal to the change in kinetic energy. That's called the work energy theorem. And the only work done on the object in this case, since there's no friction, and you're just lifting the object or object's going up, must be the work due to gravity. And another thing to understand is, why is this term canceled out? Well, if the person started down here and ended up here, the final position is has a 0 speed, so it would have a 0 kinetic energy. And as I stated previously, the work to do this is the work of gravity. So what's actually causing the work to happen? What slowed it down? Work due to gravity. Since these two works are actually equal to each other, we can set them equal to each other. And now we have mg h initial minus h final is equal to 1/2 mv squared initial. Now if you notice, the masses are on both sides of this equation, so they can cancel out. And we can solve for the final velocity like we wanted to. Now, as we put the numbers in, we can see that the numbers here are 1.2, which was the initial, minus 4.8, which is the final, which comes out to be a negative number, but that cancels with a negative and you end up with a positive. But as I started the problem with, I could have called this 0 and this 3.6 and made the problem a little bit easier. Either way, it would still come out to the same final speed of 8.4 meters per second. All right, now we're going to look at a different type of potential energy called elastic potential energy. In elastic potential energy is the energy stored in a compressed or stretched object. This would be like a slinky or a rubber band or a bow and arrow, or even pulling a ruler back. You're storing potential energy, and elastic potential energy has the ability to do work due to its position. Your book doesn't cover this type of energy until Chapter 10, Section 3, so it might be a good idea for you to, in your active reading, to include Chapter 10, Section 3. So this is the formula for potential energy elastic, and we'll derive it in the next slide. But let's look a little closer at it. K is what's called the spring constant. And the spring constant is basically how compressible the spring is. It's like, in other words, how much force you need to move it 1 meter. So it has units of newtons per meter. So a very stiff spring would have more force per unit distance needed to move it or stretch it in or out. And X is simply the displacement from its equilibrium position. Something interesting to note, though, is this can't be negative since K is positive, and any X's, even if they're negative, are going to be squared. So the negatives cancel it out, and it's always going to be positive. All right, so let's derive this elastic potential energy equation. So we have a block, and we start it out at position 1, and we compress it into position 2. Now, as you know from playing with springs and different little springs we played with when you were kids, as you push it in, it's not the same force the whole time. The more you push it in, the more force there is. So this force will vary from position 1 to position 2. So I want to know how much work we needed to compress it. And we know that force is equal to, work is equal to force times distance. In this case, well, let's call distance x. So it's force times distance. And we don't have to worry about the cosine of the angle because the cosine of the angle to the direction of motion is 0. So it just drops out anyhow. Cosine of 0 is 1. Alright, so we can't use the force at position 1 or at 2 because it varies. But what we could do is take the average between the two. And it's a linear relationship, so we could actually just find the force at each position, add them together, divide by 2, and find the average force. Okay? Okay, so the force at 1 is 0 because you haven't even started squishing the spring yet. And the force at 2 is equal to kx, which is Hooke's law. And we'll go into more detail with that at a later date. So, what would be the work done then? Well, you have at force 1 is 0, at force 2 is kx, and 1/2 to take the average, and you're going to multiply that by x, which is a distance. And you end up with the work is equal to 1/2 kx squared. And we define that work that's stored in the spring now as elastic potential energy of the spring. Okay? So let's do an example with it. A spring with a spring constant of 550 newtons per meter has a relaxed length of 2.5 meters. The spring is then stretched to a distance of 3.6 meters. What is the elastic potential energy stored in the spring? Well, we have potential energy elastic is equal to 1/2 kx squared. We put the numbers in, and x would be the final position minus initial position, and squaring it. So that comes out to be 330 joules. So those are the two types of potential energy we'll be discussing, potential energy gravitational and potential energy elastic. And we'll actually take those two types of potential energy and apply them to more complex problems dealing with conservation of energy in the later videos.